Lecture 31, and we are discussing laminar non-premixed flames, which are also known as laminar diffusion flames. I told you that they are less important from a practical point of view compared to turbulent non-premixed flames, but nevertheless they are easier to study, and we should study them first before going to turbulent non-premixed flames. And yesterday we looked at some results without deriving much of a laminar jet of fuel which is coming out into an infinite oxidizer field, quiescent infinite oxidizer field. And just some broad features of that. If you remember that we have this jet coming out, there is no combustion, so there is a non-reacting jet, and this is fuel. So we saw that we'll get an expanding jet, and we set x equal to 0 here in our coordinate system. This was 2r, that is the radius of the tube. So this is a circular tube through which the fuel is coming out. There is r, and we saw that there is a potential core. This is the zone in which the nozzle values are preserved, in the sense that velocity, fuel mass fraction, these are the same as at the nozzle exit, and this is called a potential core. This height is x c, let us say. And then we looked at some profiles yesterday of velocity as well as fuel mass fraction. And just to refresh your memory, let's look at that once more. So if you call the velocity at the nozzle exit Ve and assume it to be uniform, then you can plot Vx0 by Ve as a function of x, which is the axial distance. Now what is Vx0? This is Vx for the velocity in the x direction, and Vx0 for the Vx which is at the center line, that is at r equal to 0. So if you plot the center line velocity Vx0 normalized by the uniform exit velocity at the nozzle, then you get Vx0 by Ve, and if you plot that, you'll notice that it is 1, that is unchanged from the nozzle value, up to some height, the same height as the potential core, and then it decays. So the center line velocity decays. We saw that yesterday. And what is happening is the jet is coming out with a momentum, and that momentum gets transferred to the surrounding air. Air also gets entrained into the jet. All these things are happening. And we also looked at Vx by Ve, again axial velocity normalized by the uniform exit velocity value of Ve. And if you plot that again at the nozzle exit, that is at x equal to 0 plane, it's all uniform at the value of 1 because we have normalized with Ve. And then if you go up, if you go higher and higher along the height of the flame, then you will get a decay in the center line velocity, and also the velocity profile gets rounded. It's not a sharp top hat profile like what you get at the exit of the nozzle, and it keeps expanding. So that means if you just mentally, if you just add these, then you will get the jet contour, isn't it? That's why this is expanding, right? So this tells you that the velocity comes to 0 here, but velocity comes to 0 at some longer distance in the radial direction. So this is what we get when we have a non-reacting laminar fuel jet issuing into an infinite reservoir of quiescent air. So this is from Turns's book. He derived equations and he plotted those. We didn't derive equations, we are just looking at qualitative features. Now what happens if you set up a flame? This was not a flame. Now if you set up a flame, then you will get profiles like this. So let's see the first one. Yeah, so this one. So this is your nozzle, 2r. This is the diameter of this. This is x equal to 0 plane. And what you see are these shapes of isocontours of equivalence ratio. Okay. And this is for phi less than 1, the topmost one. Then the dashed line is phi equal to 1. Then you have a couple of others, this as well as this, these are for phi greater than 1. Okay, why are these greater than 1 and this less than 1? We don't understand this at this point of time, but we'll slowly understand that. So these are contours of equivalence ratio. And yesterday I also told you that the flame is, the diffusion flame is where phi is equal to 1. So this is the stoichiometric place, okay, where fuel and oxidizer meet in stoichiometric proportions. So that's why this is showing with a dashed line. This is the flame zone because this is where phi is equal to 1. Okay. Now let's think about various profiles like what we did for the laminar non-reacting jet, which you saw just 2 minutes back. And in this case, we want to see, for example, what happens to temperature. In the laminar jet case, non-reacting jet case, we didn't plot temperature. What was the reason? There's no point, isn't it? Because there's no reaction taking place. It's all uniformly the same temperature as the ambient. But we didn't want to do that. Pointless. Now, let's see the profiles here. At the nozzle exit, it's all VE velocity. Vx equal to VE at the nozzle exit. It drops to 0 value. So this is that same top hat profile, assuming uniform velocity profile at the exit of the nozzle. And then this is temperature profile. Temperature profile is T infinity, uniform at T infinity, which is uniform also at TF. You will see two values written. This is TF, this is T infinity. That means TF is at the center line, it's TF, and elsewhere it is T infinity. The fuel temperature is TF basically. Fuel is coming out with a uniform temperature of TF. Fuel is coming out of the nozzle. And the ambient temperature is T infinity, but TF and T infinity are the same. Okay. This is at the nozzle exit plane where really nothing is happening. But if you go higher up, so you cut this plane X, so you will get to see a temperature profile which looks like this. All right. So we can understand this because you will get this sort of temperature profile if you move, let's say, from the center line towards the flame. Right. If you move from the center line towards the flame, at the center line you will get a lower temperature. As you move in the radial direction, the temperature will keep on increasing. It will reach TF at about where phi is equal to 1. So imagine running a line, a radial line like this. Okay. Imagine you are moving from here towards the flame and then even beyond the flame. So you are moving radially outwards. So you will get a higher temperature at the flame, and then after the flame it will start dropping. And if you are sufficiently far from the center line, then you will get the temperature T infinity. Okay.
Can you explain when the phi less than 1, what is the phi less than 1 situation?
Yeah, so these are contours of phi, which you see here. So this is on this surface. This is actually not a line, right? Because this is an axisymmetric situation. So this is a surface. There is a surface which you have cut with a vertical plane, and you are seeing this line, okay, this curve. On this curve, phi is less than 1, some value. Okay, so phi less than 1 means how much? 0.7, 0.9, 0.5, 0.6, whatever. So is it for all such values? No, this is just a representative value. Maybe phi equal to 0.6 here. Okay, so some value. He has just shown this. This is all qualitative. He has shown this to tell you that phi less than 1 lies outside phi equal to 1. Okay, so this is a bigger envelope, and phi greater than 1 are smaller envelopes. Okay. Now, as I said a few minutes back, that I'm not explaining it right now, but this will become clear as to why phi less than 1 is above and phi greater than 1 is below the flame. That discussion will come later. Okay. But we are now trying to understand these profiles. So this is okay. If you move radially out, when you strike the flame, then you get high temperature. Then if you move away radially, then the temperature will drop. Fine. This is reasonable. This is reasonable because we think that this is how the profile will look like. This is some kind of an envelope. From center line towards the flame, temperature will increase. Okay. So, this plane which you see as is at x equal to LF. Now, what is LF? LF is the length of the flame. So, this surface is touching the top of the flame. Where is the flame? Flame is the dashed line corresponding to equivalence ratio of 1. So, if you run this surface, then you are getting phi equal to 1, that is the flame at the center line. So, at the center line you will get the maximum temperature. So, that is why you get temperature as a function of the radial distance, temperature is maximum at r equal to 0. And he is also marking it with Tf, so that means this is the flame temperature. And then it drops down, it will reach T infinity when you are sufficiently away from the center line. Okay. So, this is about temperature profile. Not very hard to understand.
So in premix flame, maybe I'm wrong. In premix flame, the shortest flame length we got when it is in stoichiometry. Is it correct? I mean, I've seen somewhere.
Yeah. Yeah. So, the question is about when do we get a shortest flame length when we have premixed combustion, right? Now, I think we'll skip the discussion right now. I'll just give you a hint and the details we can work out later, because then it will be too much of a diversion. How do you get the flame length in case of a premixed flame? In fact, in the premixed flame discussion, we don't discuss about flame length so much. Okay, suppose there is a Bunsen flame. So, what is the height of the cone? Did we actually explicitly derive expressions for that? But if you want, you can do that. Now, how will you do that? If it is laminar premixed flame, you will get a nice cone, then we know that SL equal to VU sin alpha. So, from that, knowing the SL value, because you know the mixture. So, if you know the mixture, you will know the SL value, and VU is in your hands. This is the velocity that you are sending. So, from that you will get alpha, right? And if you get alpha, alpha will come from the geometry, isn't it? Tan alpha must be the radius of the burner divided by the length of the flame. So, from all that you can get the height of the flame. So, think about when you will get the shortest height of the flame. So, I will leave it there. I think you can work that out yourself. Let us focus on the non-premixed flame. Okay. So, here we just discussed the temperature profiles. Let us see what else we can discuss. We can discuss the species profiles also. So, species profiles again at these 3 planes. We have these 3 planes. One is just at the exit of the burner, next one is at some height, and then there is another one which is at a height which just touches the top of the flame. Right? These are the 3 planes that we are considering. Accordingly, we have these 3 plots. So, the first one corresponds to x equal to 0, burner exit plate of the burner. YF is the top hat profile because it is the only fuel that you are sending. Through the nozzle, there is only fuel coming out. So, YF must be equal to 1 at the nozzle exit. Y oxidizer, YOX is oxidizer. OX is for oxidizer here, and that is equal to 1 outside the flame. Okay. By that, by OX I don't mean oxygen again, right? It's air. If it is coming into air, then it's air. Oxidizer, does it have to be always air? No, but usually, most of the time. So, if it is not air, it can be, let us say, a mixture of 30% oxygen, 70% nitrogen. So, if that is the case, then is our YOX equal to 0.3? No, it is still equal to 1, because your oxidizer is still oxygen plus nitrogen. Okay, so, this is the whole oxidizer, not oxygen. So, that is equal to 1, and then it drops at the rim of the burner. Now, let us see what happens if you go to an intermediate height. So, this is the YF profile, this is the Y oxidizer profile, and this is the Y product profile. Okay. So, the question is, do we understand this? What about YF? If you follow where my pen is, this is the value. This is YF value at the center line. It is less than 1, reasonable? Yeah, because the fuel would actually diffuse out, isn't it? So the center line value will decay. We know that from the non-reacting jet, but here also we'll expect the same thing. So this is YF, and then that YF comes down and it comes to a very low value, probably even 0 here. Okay. So where does it come to 0, and why does it come to 0? Yeah, so it will come to lower values obviously because of combustion. So that's the why of the question. And where? At the flame. At the flame. So again we are moving from this point, going all the way like this. When we come here, we have hit phi equal to 1 surface, and there YF must come to 0. So fuel is getting consumed.
At center line, the YS should be 1 because we have no oxidizer there, only fuel is there.
Yeah. So at the center line, why does the question is at the center line? Why YF is less than 1? Actually, I have given you part of the answer. So part of the answer is that YF will tend to diffuse out. Okay, but if YF is less than 1, then who is making up for the value? In the sense that if you add all the mass fractions, you should be able to get 1 anywhere. Anywhere, if you add all the mass fractions of all species, you should be able to get 1. How many species do you have? Yeah, so here how many species do you have? Let's answer that question first. Fuel, oxidizer and products in the simplest possible model. I have been saying that you cannot make it less than 3, right? So if you observe these 3, we have only 3, so that's why you're plotting 3. You will notice that the deficit in YF, that is YF is less than 1 by some amount, that is made up by whom? By products. Okay, so that means the products actually diffuse towards the center line. Okay, and Y oxidizer, if you look at the Y oxidizer profile, it's actually, this is actually more like 1, some distance away, because there is not much product in here, but Y oxidizer comes like this, and like fuel, Y oxidizer also comes to 0 at the flame. So this is the location. This is the location when phi is approximately equal to 1. Now let's follow this up, this sort of situation. Let's do the qualitative analysis of the profiles at the flame tip. This is the flame tip. So here you will see oxidizer going to 0 at the center line, and product from 1 diffusing outwards. Where did the fuel go? Fuel is consumed because at the center line it's 0. So there's no distribution of fuel in the radial direction. So a particle of fuel, a packet of fuel goes like this, keeps moving. Okay, some fuel will move in this direction, but keeps moving, keeps moving. The center line fuel concentration keeps decaying. Here, all the fuel is getting consumed at the center line itself. Correct? So this is Y product and this is Y oxidizer. Y oxidizer is now able to reach the center line. It has to, because then otherwise how will it consume the fuel? Okay. Now one thing that we want to learn from here is about the profiles that we get in a non-premix flame, diffusion flame. So you will let's actually for a minute let's focus on this one. Okay, the second one, and I'll try to draw this. So now we are talking about a laminar jet diffusion flame. And we are plotting this intermediate value of x which you saw, and roughly this is how it looked like. So this is Y product, this is Y fuel, this is Y oxidizer. Okay. You've already seen this, and I've drawn this again. Now, this is important to understand. This is where we suspect the reaction is taking place, correct? So this corresponds to the center line. We have moved away from the center line. Your flame is kind of like this, right? And you have moved along this direction, and you see that fuel is getting consumed here, and the oxidizer is also getting consumed here. So the way I have drawn it, it seems to suggest that there will be no fuel if you cross this surface, the fuel surface. If you go this side, there will be no fuel. And similarly, if you cross over this way, beyond phi equal to 1, if you come to the interior of the flame, then again there will be no oxidizer. Now, is this actually correct? This is in fact an idealization. It is not exactly correct. So, in reality, you will get some oxidizer which will seep like this. It will be able to cross the flame and diffuse to the other side. And in reality, the fuel mass fraction will also tend to show like this. So there will be some amount of leakage of fuel towards the oxidizer side and some amount of leakage of oxidizer to the fuel side. Okay. So the sharp profiles, the sharp drop in fuel and oxidizer mass fractions which you saw, these are not 100% realistic. These are okay, but this does assume something. So purely from your intuition, purely from just some understanding of combustion, can you say why this drop to 0 is unlikely? It's not a bad approximation, but in reality there will be some amount of leakage. Why?
Because when at high temperature, as we earlier also discussed, temperature will be higher near the flame inside, so oxidizer will tend to diffuse to initiate reaction somewhere near inside the flame.
Okay, if I understand you correctly, I think what you were saying is the fuel is moving from the center line towards the flame, but as it moves towards the flame, because of high temperature, some of the fuel will break down. Is that what you're saying?
Some of the fuel might tend to initiate reaction with the oxidizer, so oxidizer will also diffuse.
But how will the oxidizer get there at the first place?
Diffusion.
The question is this. I am asking, do you expect a leakage of fuel towards the oxidizer side and an leakage of oxidizer towards the fuel side, or do you not expect? What is more likely? Will there be leakage or will there not be any leakage? There will be leakage. So what tells you that there will be leakage?
But fuel temperature will be high because burning is there inside the flame. Temperature is very high. The density will be less. And outside the air which is there, the density is high. So that due to high temperature, density is less. It will try to move up with the natural thing, and the air is heavy. It will try to move.
So you are saying that because of density differences there will be a leakage. But I mean, who is consuming that fuel and who is consuming that oxidizer? This fuel is getting consumed and oxidizer is getting consumed. Who is consuming them? Product is not consuming, right? Products are getting produced. Flame. Flame is consuming this. So you have this flame here, and you have fuel coming from this side, you have oxidizer coming from this side. When is it likely that oxidizer will go this side and some amount of fuel will also come this side? When is that likely? When is that likely? Is it likely when the flame is strong, or is it likely when the flame is weak? Flame is weak. Okay. When the flame is weak, some oxidizer will pass. If the flame is weak, some fuel will leak through. Okay. Now, what do we mean by weak or strong?
The consumption rate is low. Weak means consumption rate is low.
So, weak essentially means that the rate of reaction in the flame zone is not very high. So, if the fuel goes to the flame at a rate which the flame cannot handle, so to speak, then some fuel will move to the other side, to the oxidizer side, unreacted. It will just diffuse out. Okay, so you have a consumer, you have like a giant who can eat a lot, and you are supplying fuel from here. If this is really a giant, it will be able to consume whatever you supply. Then there is no leakage. And if there is oxidizer coming from this side, and again if this is a giant, he will be able to consume everything, and then there is no leakage. So by giant I mean a strong reaction zone. If it is not so strong, then there will be leakage, right? Unless we talk about an infinite reaction rate, okay, in the flame zone, unless we talk about an infinite reaction rate in the flame zone, there will always be some leakage. Reaction rates are finite. Okay. If reaction rates were infinite, reaction times would have been 0. Okay, but we know that the reaction times are not 0. There is some chemical time scale. Some chemistry is happening at the flame. It can be very fast. A very fast reaction, combustion reactions are typically fast. So, they will give you chemical times of the order of milliseconds or even lower, right? But they are still, the reaction rates are still not infinite. If the reaction rates are not infinite, some fuel will come and escape the flame and move over to the other side. Similarly, some oxidizer will come and escape over to the other side. Okay, so it depends on the reaction rate. So, these sharp profiles which you see in this plot, these can be assumed if the reaction rate is assumed to be infinite.
Can we relate this with rich and lean mixture?
Okay, so the question here is, can we relate this to rich and lean mixture? Okay, so we have to see this question in detail, but what do you think? It should, right? It should matter. It should matter because the reaction rate will depend on whether the mixture is rich or lean. Okay, but then there is a problem. I mean, this is not a mixture that you are sending, right? Are you sending a mixture? It's not a premixed line. You are sending only the fuel. Okay, so what is rich? What is lean? In any case, the flame is at a place where phi is equal to 1. Okay, so his question is good. He is thinking that okay, if it is rich, then there will be too much of fuel, and the flame will be weak, and then more fuel will leak through. All right, but see, flame is at phi equal to 1.
I want to say that there is the mass flow rate of the fuel and there is the mass flow rate of the oxidizer. Suppose if the mass flow rate of the oxidizer is greater than that of the fuel, then
Okay, so we haven't really discussed a mass flow rate of oxidizer in this case. We are talking about a situation when we are sending a flow rate of fuel through this and in a quiescent infinite oxidizer field. Okay, so the oxidizer is present in abundance and there is no flow rate of the oxidizer. So the fuel just comes, whatever rate you send, the fuel will come and it will give you a flame. Where is the flame? The flame is where roughly phi is equal to 1. Okay. So in order to answer your question in more detail, we have to see a situation then there is a fuel flow rate and there is an oxidizer flow rate. So we can't discuss that right now, isn't it? Because there is no oxidizer flow rate. Oxidizer is present in abundance. But what will happen if you change the fuel flow rate, if you increase it? We saw that yesterday. Yesterday towards the end we saw that the length of the flame, and I wrote an expression for that without deriving it. The length of the flame is proportional to QF. What was QF? QF was actually the flow rate of fuel through the nozzle. So QF is increased, then the length of the fuel will increase. So that means if you increase the mass flow rate of the fuel, as Karthik was asking, then the flame height will increase. That much we know, but it will, the flame will still be able to find a phi equal to 1 surface, right? It will still be able to find a phi equal to 1 surface, and a phi equal to 1 surface is neither rich nor lean. It's actually stoichiometry. So this is a qualitative discussion that we wanted to have on non-premixed flame. So here we understand that there are major differences with premixed flame kind of situation, because in a premixed flame you do not have fuel coming from one side, oxidizer coming from one side, and that's why this is important to learn, to be able to learn to interpret profiles. If you do diffusion flame measurements, if you measure temperatures at different heights, and if you measure mass fractions of various species at various heights, then you should be able to interpret this. In fact, if you have something like this, if you measure, then from that you will be able to say that the flame is approximately here. I keep on saying approximately because unless the reaction rate is infinite, the flame surface is not thin. Correct? See, here you can say the flame is exactly here where the tip of my pen is. It's exactly here. You can say that because these are dropping to 0 exactly at that location. That means when sketching these profiles, we have assumed the reaction rate to be infinite, and that also will mean an infinitesimally thin flame. Infinitesimally thin flame. Correct? But real flames are not infinitesimally thin. The real flames, in a real flame, I will draw this again. In a real flame, you will have Y fuel, Y oxidizer. This is the infinite reaction rate situation. In a real flame, it's more like this, or like this. So the flame zone may be thicker. Actually, the amount of leakage is not so much. It will not go this far. It will not be this high. I have drawn it in an exaggerated scale so that you are able to understand. So the flame, you cannot say the flame is here in that case because there is leakage. So the flame is more like this, again exaggeratedly shown. So again, coming back to what we are doing, what I told you yesterday, that we are studying laminar jet flames, laminar jet diffusion flames, non-premixed flames. What is our objective? Our objective is to get all these profiles. One of our objectives. We want to get temperature as a function of r and x, then all velocities, if you have velocities vx and vr as function of r and x, and then these mass fractions. At least 3 mass fractions we have in mind: y fuel, y oxidizer, and y products as function of r and x. Okay, so that's one objective. The other objective is, a concurrent objective is to get the flame length. And I'll just repeat what I said, that if you want to design a burner, then you should be able to say that, okay, I have this fuel is coming out from here, and this is the expected flame height. This is the expected flame height. You should be able to say that. Otherwise, let's say if you're heating something which is here, you will not know whether your flame height is appropriate or not. It may be too large or it may be too small. This is one motivation. So we want to know the flame shape, the flame size, and all these profiles. That is the objective of the work that we are doing. Now, contrasting this with laminar premixed flames, in laminar premixed flames we could actually derive laminar burning velocity. That was more of an objective for us, because that was a fundamental property of premixed flames. Laminar burning velocity is a fundamental property of premixed flames, and we saw that when we went to turbulent premixed flames, there also we used laminar burning velocity. St equal to SL plus something. Remember that? Okay. So getting laminar burning velocity was important when talking about premixed flames, and we did primarily laminar premixed flames. But what about laminar non-premixed flames? Is there a burning velocity?
Yes, because we have a mass flow rate, and we can calculate the area, surface area of the flame
Okay, so the response that I am hearing here is that we have an m dot of the fuel, then we have a flame area, so we have some density, so we can do m dot divided by rho divided by area to get some kind of a velocity. Okay, but there is a problem because the m dot that you are giving is actually the m dot of the fuel. It's not the m dot of a mixture. So that's one problem. Secondly, this flame doesn't really have a fundamental velocity. Okay. Non-premixed flames do not really have a fundamental velocity. Premixed flame does have a fundamental velocity. Why do I say this? Again, same old example, fuel air mixture in a tube, transparent tube, you ignite it here, you see a flame which moves. We discussed how it moves. It heats the mixture and supplies the active chemical species ahead of it to ignite another zone, another zone, another zone. That's how the flame moves. We know that. And we know that this is a fundamental characteristic of premixed flames. Right? You may be able to stabilize the flame on a burner when it will actually appear to be stationary. It is a stationary flame if you look at the conical flame that you get on a Bunsen burner. But it still would have moved if, in fact, if it does move, if you abruptly shut off the fuel flow, it will come back and things like that. So it has a fundamental tendency to move. A diffusion flame will not have a fundamental tendency to move, isn't it? It will actually try to sit at a position where phi is equal to 1, isn't it? That's the location which we were showing with the dashed line. That is the location where it will tend to have the mass flux of the fuel and the mass flux of the oxidizer in stoichiometric proportions. So it doesn't really have much of a reason to move. Okay. In a transient sense, when you have fuel and oxidizer and if you igniting it, then in that short period of time there will be a flame which will just move and settle at phi equal to 1 surface. That movement is there, but otherwise there is no fundamental tendency of a diffusion flame, a non-premixed flame, to move like that. So there is no fundamental burning velocity. And in any case, what I was telling you is that if you do m dot divided by rho a to get the velocity, that m dot is that of the fuel, so it's not a mixture property anyway. Okay, like laminar premixed combustion, that was a mixture property. Laminar burning velocity is a property of the mixture. Okay, so we know our objectives to get the profiles, get the flame shape, flame length, and we'll have to see how to do this. For the premixed flame case, we did just laminar burning velocity, and we got an expression for it. In fact, we did few more derivations where we got a minimum ignition energy in one case when discussing ignition, and we also got the quenching distance in one case when trying to analyze the process of quenching. Quenching distance was also important, so we could derive some relations. In case of this non-premixed flame, we will not be able to actually work through an entire derivation for the interest of time. We will not have that much amount of time at our disposal to, in fact, solve all equations, get temperature, velocities, fuel mass fraction, oxidizer mass fraction, product mass fraction, everything as a function of the spatial coordinates, r and x. We will not have the time to do that. If we could get all the profiles, we could have also got flame length, right? We will not be able to do this. So our purpose will be primarily to understand how diffusion flame problems are solved. Okay. So I'll give you a scheme, give you the scheme of things, the way equations are handled to be able to get a solution for a laminar non-premixed flame without actually solving equations. That is the objective. The other objective is that we will take the available results in the literature and look at expressions for flame length and see what happens if you calculate flame length from available expression and compare flame length obtained from experiments. How are your predictions of flame length calculations? How good are those compared to known experimental flame lengths? So that's all we are going to do. Now, when it comes to laminar non-premixed flames, actually 2 or 3 things. One is that you have to be a little patient because this will run into a few lectures. It will be long, so that is one reason. The other reason you have to be patient is that it will be somewhat mathematical, and there is a third reason for you to be patient also. That is, I'll have to change the notation a little bit, so you have to be careful. Okay, so a lot of things it will require your patience, and I'll use a different book which I think I didn't list before. So this book is in the second or third edition. I have a first edition book. This is by Poisson. Is that okay? And so it's not Poinsot. Okay, you ask him; he knows the best. And Dennis. What is that? Venant? Venant. Okay. So Poisson and Venant. These are both professors in Toulouse and École Centrale Paris. Okay. So this is a book, and this is a highly mathematical. I mean, it's more like theoretical aspects of diffusion plane. So our notations will change a little bit, but as and when we change notations, I'll let you know. So the first thing that we are going to do is actually forget about the jet flame solution for a moment. Okay. For a few minutes, we'll not think about it. For maybe half an hour, we'll not think about it. The 10 minutes that we have today, as well as part of tomorrow's lecture. So we'll talk about some tools that we require to analyze idealized non-premix flames. So I'll introduce the concept of passive scalars and mixture fraction. Passive scalars and mixture fraction. So we'll slowly learn this. What I did was I followed the notation used in this book. Okay, and I'll give you some handout which you can use. I thought that if I translate notations from this book to the notations which we used so far from Turns's book, that may or may not help you, because if you get the book, if you get some chapters of the book with you, and then if you get my notes, it will be easier for you to follow the book. Okay, so we are adjusting notations to the book that we are using the same notations that we are using in the book. So passive scalars and mixture fraction. How do we proceed? We'll look at the various species profiles, species equations first. Now, this is what is happening. Nu is this equation coefficients, stoichiometric coefficients. So nu f times fuel, and nu, this is O for oxidizer now, not for oxygen. We were using OX for oxidizer. Now I am making this O as oxidizer. And P for product, not PR. Okay. I didn't tell you another difficulty. That is, I'll give you some conservation equations, and essentially without deriving, but I trust that you will be able to actually follow this, because we have some idea about combustion conservation equation so far. So, let us write the conservation equation for species yk, not writing yi, writing yk, y for mass fraction, k for the kth species. So, all right. So, this is the equation. Is it possible for you to appreciate this from all your prior knowledge of conservation equations? I hope so, because there is a transient term, okay, and then there are these terms. Actually, this is not one term. When I write del xi, it can be del x, del y, del z. So, there are 3 coordinate axes x1, x2, x3. So, all 3 together as written as del xi of rho ui yk. So, you have seen this form of conservation equation before. So, the velocity is included here. So, advection effects will come through this, and then there will be a diffusion term which will involve the second derivative. So, this is del xi of rho d del yk del xi plus omega dot k. Omega dot k must be the source term, which is the reaction term. So, the omega dot k is actually we will define that in more detail slightly later, but it is of course the reaction term, it has to be. So, what that means is that there is a transient change in the mass fraction of the kth species, and that is related to the advection of species, but also diffusion of species, plus also there is chemical reaction taking place. So, this is how everything is put together. It looks shorter than what the reaction is, because we are using this notation where we are writing del xi, but it can have multiple components of xi. Okay. So, this gives you a yk species equation, and we will just start maybe. Okay. We will not have a lot of time today, but I'll just briefly describe what is our chemical system. Our chemical system is again, this is familiar, but in a slightly different notation. So, this is a compact notation for these reactions, and we used something like this first when we were discussing the law of mass action. So, these are the coefficients of various species. The species are shown with this curly m. So, how many species are there? Capital N number of species. So, that is why we are adding for n. Remember, we used to take all species. So, if we when we started discussing law of mass action, we said that okay, maybe H plus O2 gives you OH plus O. So, there are 4 species. We will write all 4 species on the left hand side and all 4 species on the right hand side, and then some coefficients will become 1 and some other coefficients will be 0. Remember that? So, we will write all species. So, how many species do we have in this system? This is a more general thing that we are writing. I am not saying that there are 3 species or 5 species or whatever. So, there are n species, and if you have n species, then all n on the left hand side, all n on the right hand side also. And the reactant side, the left hand side, the reactant side is denoted with a prime, so nu prime Kj, and on the product side, on the right hand side, it's nu double prime Kj. So, how many species? Capital N. How many reactions? That is M. So, J goes from 1 to M. Okay. So, in this summation, this K controls this first subscript, and this J is controlled by the reaction that you were talking about. So, there can be multiple reactions. So, multiple species participating in multiple reactions. Okay. So, how many reactions? Up to M. I think I will prefer to stop here actually, because the rest of it I can't do in the next 2 or 3 minutes.
Mu dash was in the reactant side.
On the reactant side. Nu double prime is on this one, and maybe just we can do one step, that is the same thing can be written as we can write this. Where does W come from? What is W? Molecular weight of the K species. So, you can do based on this chemical system that we have, you can do a mass conservation. So, the blue one which you see here is the chemical system, and the one which I have written in red must be mass conservation. Correct? So, you can easily do a mass conservation from here, but then if you take both on the same side, then you will get a difference of nu double prime and nu prime, which will give you a mass conservation like this. So, I will stop here, and we will start from this tomorrow. Thank you.